46 years ago, this mountain killed 57 people in the deadliest volcanic disaster in American history. That alone is enough to make any new earthquake beneath Mount St. Helens feel like the beginning of something terrible. And now, once again, the mountain is shaking. Small earthquakes have been clustering beneath it for months, enough to trigger a fresh wave of fear, fresh headlines, and the same question people always ask when this volcano starts to move. Is it waking up again? But the strangest part of the story is not the shaking. It is what the ground above the volcano is doing at the exact same time. Instead of swelling upward, instead of bulging like a volcano preparing to erupt, the surface has been quietly sinking. That should not fit the simple version of the story people carry in their heads. Earthquakes plus a volcano are supposed to mean magma is rising. Rising magma is supposed to push the mountain up. But the data here is pointing in a different direction. And that difference matters, because if you misunderstand what this mountain is doing now, you will misunderstand the moment it truly becomes dangerous later. Stay with me, because by the time this is over, you will know exactly why scientists are not calling this an eruption countdown, exactly what kind of activity they believe is really happening underground, and exactly which warning signs would actually tell us the situation has changed from strange to serious. Right now, Mount St. Helens is not under an eruption warning. Its official alert status remains normal, and its aviation color code remains green. That is the most important thing to say clearly before the imagination starts running ahead of the science. No agency is forecasting an imminent eruption. No official monitoring network is telling people that a blast is about to happen. But that does not mean the current activity is meaningless. It means it has to be understood correctly. The mountain is alive. It is being watched around the clock. And the pattern showing up beneath it is scientifically interesting precisely because it looks unsettling at first glance, and yet does not match the pattern of a volcano about to blow. That is why this story matters. Not because the mountain is exploding right now, but because it is doing something subtle, something real, and something most people would misread if they only looked at the word earthquake and ignored everything else. Since early this year, monitoring agencies have recorded hundreds of small earthquakes beneath Mount St. Helens. By early summer, the rate had climbed to several dozen located events per week, and almost all of them stayed below magnitude 1. That sounds dramatic until you understand what that number really means. A magnitude 1 earthquake is tiny. It is not the kind of quake that knocks things off shelves or sends people outside. In most cases, it is not even felt by anyone standing nearby. These are instrument earthquakes, not human earthquakes. They are signals that show up clearly on sensitive monitoring equipment, but not in everyday life. And that detail is important because the human brain reacts badly to raw accounts. When people hear hundreds of earthquakes, they imagine something loud, unstable, and escalating toward disaster. What scientists actually see is a cluster of very small events deep beneath a volcano that has produced similar behavior before. That does not make the swarm irrelevant. It just means the meaning of the swarm depends less on the number itself, and far more on where the quakes are happening, how deep they are, how they change over time, and what the rest of the mountain is doing at the same moment. And that is where the story becomes genuinely strange. If magma were forcing its way upward into the shallow part of the volcano right now, the most obvious physical response would usually be inflation. The surface would rise. The crater area, or surrounding flanks, would begin to swell as underground pressure pushed the mountain outward. But Mount St. Helens is not doing that. Instruments tracking deformation have shown the opposite trend. The surface has been settling downward, very slowly, very quietly, but consistently. So now we have two facts sitting right next to each other that seem impossible to reconcile if you are only using instinct. The volcano is shaking, but the ground is sinking. Earthquakes suggest underground motion, but the surface is not behaving like magma is charging straight upward. That apparent contradiction is the key to the whole puzzle, because once you understand why both of those things can be true at the same time, the entire story changes from panic to pattern recognition. To make sense of that pattern, you have to forget the cartoon version of a volcano. Mount St. Helens is not a single chamber of molten rock sitting directly beneath the crater like a pot on a stove. It is part of a much deeper and more complicated plumbing system that extends miles into the crust. Fresh magma is generated far below and can begin moving upward very slowly, collecting in deeper storage zones before it ever gets close to the surface. When that deeper system begins to recharge, pressure increases within the surrounding rock. Fluids move, old fractures are stressed, tiny breaks and adjustments happen as the crust responds. Those adjustments produce small earthquakes. Scientists have a name for this type of activity. They call it a recharge swarm. That term matters because it tells you exactly what they believe the mountain is doing. Not erupting, not racing toward the surface, recharging, refilling, quietly rebuilding pressure deep underground in a way that can continue for years without producing an eruption at all. That distinction is not just academic, it changes everything. An eruption countdown and a deep recharge phase can both involve earthquakes, but they do not look the same once you study the details. In a recharge phase, earthquakes often stay relatively deep, remain small, and occur without the surface beginning to rise in a dramatic way. In an actual pre-eruptive sequence, the pattern becomes much more aggressive. Earthquakes migrate upward. The character of the shaking changes. Gas emissions increase. The surface starts to inflate. The whole mountain begins to move in a coordinated way that points toward shallow magma intrusion rather than slow, deep storage. Right now, Mount St. Helens is not showing that coordinated pattern. What it appears to be showing instead is a deep system taking in fresh material, while the shallow upper part of the volcano continues a very different process, one that explains why the ground can keep sinking even as the deeper plumbing remains active. That shallow process is the missing piece most alarming headlines leave out. The upper portions of a volcanic system do not simply freeze in place after an eruption ends. Lava domes cool, hot rock contracts, gas escapes. Freshly erupted material settles under its own weight, cracks close, structure adjusts. In other words, the top of the volcano can slowly sag even while deeper zones are gradually repressurizing below. Those are not contradictory motions. They are motions happening at different levels of the same system. Deep down, the engine may be quietly charging. Near the top, the cooled volcanic skin may still be shrinking and settling. Once you understand that, the paradox disappears. The mountain can be refilling from below while still settling from above. The sinking does not mean the deep system is empty. It means the shallow system is cooling, compacting, and relaxing faster than the deeper recharge is pushing surface deformation upward. That is why the current picture feels so strange on paper. The mountain is behaving like two stories of the same building are moving for different reasons. There's another reason people misread this kind of swarm, and it has to do with how earthquake numbers are reported. The public often assumes the official earthquake catalog is a complete list of every single seismic event happening under a volcano. It is not. Monitoring networks formally locate only the events they can detect clearly enough across multiple stations to assign a reliable position and magnitude. That means the catalog is conservative by design. Plenty of extremely tiny signals may show up as wiggles on raw traces without ever becoming fully confirmed located earthquakes. That does not mean anyone is hiding activity. It means volcanoes are noisy places. Wind can create vibration. Rockfall can mimic signals. Distant earthquakes can blur the data. Ice cracking, water movement, and ordinary environmental motion can complicate the picture. Scientists would rather undercount uncertain micro-events than fill the official record with bad data. In fact, during past swarms at this same mountain, researchers openly stated that many more tiny events were occurring than could be formally located. That is not secrecy. That is transparency about the limits of detection. And this is not the first time Mount St. Helens has behaved this way. That is one of the most important facts in the entire story, because history gives us context that fear alone does not. In 2016, the volcano produced a similar swarm of small earthquakes over a period of weeks. Again, the events were tiny. Again, many were too weak to be formally located. Again, the interpretation pointed toward deep recharge rather than imminent eruption. And after all the worry that kind of swarm naturally creates, nothing dramatic happened. The mountain did not explode. It did not suddenly transition into a 1980-style crisis. The system quieted back down, and the episode became another example of Mount St. Helens, reminding everyone that active volcanoes do not need to be erupting to be geologically busy. That history matters, because it shows the present swarm is not automatically a unique emergency. It fits a pattern the volcano has shown before. But there's another historical lesson here, and it may be even more important. When Mount St. Helens did erupt again after 1980, particularly during the 2004 to 2008 episode, the style of activity looked nothing like the famous catastrophe most people imagine every time they hear the mountain's name. Instead of a sudden sideways blast destroying forests across a huge area, it produced a slow, grinding extrusion of thick lava that built a dome over several years. It was still volcanic activity, it was still serious, but it was monitored and very different from the iconic 1980 disaster burned into the public memory. That matters because people tend to collapse all possible volcanic futures into one mental image. They hear Mount St. Helens and see the 1980 blast. The real range of outcomes is much wider than that. A volcano can recharge for years, erupt slowly, or remain restless without producing the kind of explosive catastrophe people fear most. And, in the case of Mount St. Helens, that recharge can take a long time. Before the 2004 eruption began, the mountain had been quietly recharging for many years. Not days, not weeks, years. That is a crucial timescale to remember because it completely changes the emotional meaning of the word activity. Activity does not always mean countdown. Sometimes it means maintenance. Sometimes it means the deep system is taking in fresh magma on a schedule far too slow for human instincts to interpret correctly. We are built to react to immediate threats, to loud signals, to fast escalation. Volcanoes often do the opposite. They conduct slow underground business for decades, then shift only when a much more specific set of shallow warning signs begins to line up. The problem is that most people do not learn to distinguish deep restlessness from shallow crisis. They just hear earthquakes swarm and imagine the worst. That is why 1980 remains so important, not as a fear trigger, but as a measuring stick. If you really want to know whether current activity is routine or dangerous, you have to compare it to what a real pre-eruptive countdown at Mount St. Helens actually looked like. And the 1980 sequence was not subtle. It did not whisper. It shouted. The reawakening began with earthquakes and steam explosions, but it escalated into something physically visible on the mountain itself. The north flank began to bulge outward at an astonishing rate, roughly 5 feet per day at times. Over the course of the crisis, the deformation added up to hundreds of feet. But that is not quiet settling. That is a mountain visibly changing shape under pressure. The earthquakes also changed in a meaningful way. They became part of a broader pattern of shallowing unrest linked to magma forcing its way into the volcano's upper structure. In other words, 1980 gave scientists the textbook example of what a real countdown looks like when a volcano is no longer simply alive, but actively moving toward eruption. Then came the moment that defined the mountain forever. On the morning of May 18, 1980, a magnitude 5.1 earthquake triggered the collapse of the unstable north flank. That collapse became the largest landslide ever recorded on Earth. In an instant, the pressurized system inside the volcano was uncorked. The lateral blast that followed tore across the landscape, flattening forests, destroying everything in its path, and killing 57 people. The summit was dramatically reduced. Ash spread across the region, and one of the enduring tragedies of the disaster was that even experts monitoring the volcano underestimated how far and how violently the lateral blast could travel once the flank gave way. That is why the event still haunts every new headline about Mount St. Helens. It was not just an eruption. It was the eruption that taught modern America how deceptive volcanic danger can be when a mountain changes mode faster than people expect. Now put that 1980 pattern beside what the mountain is doing today, and the contrast becomes impossible to ignore. In 1980, the surface was bulging outward rapidly. Today, it is sinking. In 1980, the unrest escalated in a visible, accelerating, shallow way. Today, the earthquakes remain tiny and deep. In 1980, multiple warning signals began stacking together in the same direction. Today, the signals point toward deep recharge paired with shallow deflation, which is a very different picture. That does not mean Mount St. Helens is safe forever. No active volcano earns that word. It means the current activity does not resemble the signature of an imminent eruption. The more honestly you compare the present to the real historical benchmark, the harder it becomes to defend the idea that this is some hidden eruption crisis quietly unfolding right now. So why does Mount St. Helens keep coming back into the conversation more than so many other volcanoes in the Pacific Northwest? Part of the answer is historical memory, but part of it is geology. Mount St. Helens is the most active volcano in the Cascade Range, and the Cascades exist because of one of the largest tectonic machines on Earth. Off the Pacific Northwest coast, the Juan de Fuca Plate is being forced beneath the North American Plate in the Cascadia subduction zone. As that slab sinks into the mantle, water trapped in the descending rock is released into the hotter material above, helping generate magma. That magma rises through the crust and feeds the chain of volcanoes stretching through the region. Mount St. Helens, Rainier, Adams, Hood, Baker, Shasta, they are all surface expressions of that much larger offshore engine. Mount St. Helens just happens to be one of the most active and most closely watched outlets in the whole system. And there's another reason this particular mountain commands attention. The magma it produces tends to be silica-rich and viscous. That means it is thick, sticky, and better at trapping gases than runnier magma types. Thick magma does not flow as easily. Pressure can build. Gases can remain trapped longer. When release finally comes, eruptions can be more explosive. That makes Mount St. Helens a volcano people are right to respect. It is not simply another mountain with occasional steam and harmless lava fountains. It is a volcano with a demonstrated capacity for violent behavior under the right conditions. That is exactly why even a modest swarm beneath it becomes a national story. The danger is not imaginary. It is just being misread when every sign of life is treated like immediate evidence of eruption. And this is where the story becomes truly useful for viewers, rather than merely dramatic. Scientists are not helplessly guessing about how they would recognize a real countdown if one began. They already know the most important signs to watch for, because the volcano has shown them before, and because modern monitoring is far more sophisticated now than it was in 1980. If the situation at Mount St. Helens were truly shifting from deep recharge to shallow eruptive unrest, several specific changes would almost certainly begin to appear together. Earthquakes would start migrating upward rather than remaining deep. The character of the seismicity could change, with volcanic tremor or more continuous fluid-driven signals appearing instead of mostly tiny, brittle fracture quakes. The long-term sinking trend would likely reverse into measurable uplift or inflation. Gas emissions, especially carbon dioxide and sulfur dioxide, would become more significant as magma rose closer to the surface, and shallow steam-driven explosions or other hydrothermal disturbances could begin showing that the upper system was being disturbed directly. The key is not just one sign, it is the combination. A genuine countdown announces itself by lining up multiple warnings in the same direction. Right now, Mount St. Helens is not doing that. It is shaking, yes, but the earthquakes are small and deep. The surface is still settling rather than inflating. The official alert level remains normal. No eruption warning is in place. That is not a contradiction. It is the actual scientific reading of the present moment. The mountain is active, but not escalating toward eruption in the way people fear. It is behaving like a living system between eruptions, not like a volcano entering the final hours before a blast. That difference may sound subtle, but it is everything. A person who does not understand it will react to every headline as if disaster is imminent. A person who does understand it will know how to separate real change from familiar restlessness. It also matters that Mount St. Helens is one of the most heavily monitored volcanoes in the world. This is not a mountain being watched casually from a distance. It is surrounded by a network of seismometers. Satellite radar can detect tiny changes in ground movement. Gas measurements can reveal changes in volcanic emissions. Geodetic instruments track deformation with extraordinary precision. The entire monitoring system exists partly because of what happened in 1980 and the lessons learned from it. That means the current calm official interpretation is not coming from neglect. It is coming from extremely close observation. The reason scientists are not sounding the alarm is not because they are missing the signs. It is because the signs they would need to see for a real countdown are not there yet. That point is especially important in an age when alarming clips and dramatic headlines spread faster than context. A mountain with a tragic history, a recent swarm, and the word activity in the title is almost perfectly engineered for public overreaction. But volcano monitoring is not a guessing game built on intuition. It is a comparative science. Researchers look at patterns, not isolated details. They ask whether unrest is getting shallower, stronger, hotter, gassier, more deformational, more coordinated. A volcano can shake without swelling. It can recharge without erupting. It can remain restless for years and still not be close to the kind of event that makes history books. Mount St. Helens is one of the clearest examples of that truth, and that is part of why the story is so fascinating. It challenges the public instinct to equate any sign of movement with immediate catastrophe. If anything, the current swarm is a reminder of how deceptive quiet can be in both directions. Sometimes people look at a calm mountain and assume it is dead when it is not. Other times, they see a scientifically ordinary burst of unrest and assume disaster is close when it is not. Mount St. Helens resists both mistakes. It is not asleep forever, and it is not about to erupt just because micro-earthquakes have returned. It is doing what active volcanic systems do between major events. It is adjusting, refilling, cracking rock at depth as pressure changes beneath a surface that still reflects the cooling legacy of its last eruptive chapter. That may not sound as sensational as an eruption countdown, but it is actually more impressive in a scientific sense. We are watching a volcano remain alive without crossing the threshold into crisis. That is not boring. That is the real story. And maybe that is the most useful takeaway of all. The most dangerous misunderstanding about volcanoes is not simply panic. It is bad timing. It is reacting too hard when the signals are routine and not hard enough when the signals truly change. That is why knowing the difference matters. Right now, the mountain is giving us a lesson in patience. It is saying that earthquakes alone are not enough, that a living volcano has many moods between silence and eruption, that the word active does not always mean immediate danger, and that the real skill in reading a place like Mount St. Helens is not spotting movement. It is spotting the moment movement changes character. So where does that leave us now? It leaves Mount St. Helens exactly where scientists say it is, a closely watched active volcano in a normal alert state, producing a small, deep swarm that fits the pattern of recharge much better than the pattern of eruption. It leaves the surface still subsiding rather than inflating. It leaves the dramatic 1980 comparison useful as history but misleading as a model for what is happening today. And it leaves us with a better question than the one most headlines encourage. Instead of asking whether the volcano is about to blow, the smarter question is whether the current unrest is staying in the category of deep refill or beginning to migrate into the category of shallow countdown. Right now, it remains firmly in the first category. The mountain that once killed 57 people is shaking again, yes. But that is not the same thing as saying it is erupting again. The data says something more nuanced and, in a strange way, more interesting. Deep below the surface, the system may be quietly taking on fresh magma. Near the top, the ground is still settling as older material cools and contracts. Tiny earthquakes are marking stress changes in the rock, but not the kind of upward moving crisis that defined the lead up to 1980. That is why the official status remains normal. That is why scientists are watching, not warning. And that is why the real story at Mount St. Helens right now is not that a disaster has begun. It is that a dangerous volcano is alive, active, and doing exactly what living volcanoes do between major chapters, reminding us that the difference between ordinary unrest and a true countdown is not fear, it is pattern. When the next real countdown begins at this mountain, it will not look like this. It will not be just deep micro-earthquakes under a sinking surface. It will be louder, shallower, more coordinated, and much harder to explain away. Until then, the honest reading is the most valuable one. Mount St. Helens is restless, not eruptive, active, not escalating, interesting, not imminent. And understanding that now, before the signals truly change, is exactly what will help you recognize the difference between another false alarm and the day this mountain really starts moving toward its next dangerous act.